we can get started. So it's my great pleasure to introduce Professor Aaron Elmore from the University of Chicago. Aaron did his PhD from UC Santa Barbara, and after that he went to MIT to do a postdoc under Professors Mike Stonebraker and Sam Madden. And then he joined the faculty of University of Chicago, and currently he's an associate professor. Aaron's main research interests are about data management, databases, all different aspects of data. In particular, he's more on the system side. Some topics include compression. He gave a talk, very nice talk yesterday about compression, about incremental computation, database as service. Some of them even came from here. Aaron received many awards. One of the examples is the prestigious NSF Early CAREER Award. So today, Aaron is going to talk about one of the systems he's been building, CrocodileDB. Without further ado, let's welcome Aaron.
Thanks, Jim. Everyone, so I talk fast, so if anyone needs to interrupt to ask a question, feel free to interrupt me. Also, this is a database-centric talk. It's aimed for a general purpose audience, but if there's any point of confusion, just feel free to ask. So great, so thanks, Jen, and thanks everyone for being here today. So databases tend to be pretty eager things. And what do I mean by this? Well, a traditional database, like a batch database, where it just kind of sits idle and waits for a user to give a query, it sits there, and when the user gives the query, the database basically does everything it can do to answer that query as fast as possible. Over the last few decades, we've seen kind of streaming systems, or kind of what we call as incremental view maintenance systems, that have basically people that have registered queries with these databases, and those queries sit there. And as soon as a record or a small set of records arrives at the database, these databases tend to more or less do everything they can do to immediately process that record or that small set of records to update these reviews. So they're eager, right? They just do stuff to kind of get answers fast because people want answers fast. But as we know, data keeps growing, growing, growing. And this eager execution model is problematic in a few different environments. One of them is the cloud. When we go to the cloud, we have typically a pay-per-use model. So when you're eagerly doing something, you're incurring some form of cost. That results in people spending money. There's a lot of environments where people have a shared, fixed amount of resources. I own this rack is shared between different tasks. So as I run these aggressive, eager queries, I am consuming resources from other things that can't run. I'm taking those resources. We're also seeing data being deployed on more edge IoT devices, and so there's a battery life associated. So as you use computation eagerly, you're actually causing that device to run out of battery quicker. And as I'm sure most of us are aware, there's environmental concerns, right? Data centers contribute a significant portion of the power consumption in the United States, and data is a significant part of these. I just saw an interesting talk from Google where they talked about how they updated their sorting algorithm and how many computation cycles it saved, and Google was happy because they could equate this with a bottom line. But just for environmental concerns, this eager execution model means I am using more power and consuming resources that people care about. And all of these things get coupled with very limited attention. I'm doing this work eagerly, I'm updating things, results that might not actually ever get looked at. So we've been really thinking about this kind of context of what you might think is a dashboard. What we might say is there's regularly scheduled queries that are going to be running at fixed intervals, and underneath there's dynamic data that's changing. There's new data that's flowing into the system, and I have reports that are potentially run daily, minutes, hourly. So I'll get more into this in a little bit, but the idea is that there's data changing underneath, and we have queries that are registered with the system, and they're going to be executing, at fixed intervals. But before we get into things, I want to do a quick primer on Databases 101 to make sure everyone's on the same page for this talk. So databases typically work as there is a structured query language, SQL, or SQL, however you want to say it, that comes in. It's a declarative query language, right? It says what I want to do, not how I want to do it. This comes in, it gets parsed, it gets typically converted into some form of a tree, an abstract syntax tree, whatever you want to call it. Sorry, my clicker's a little laggy. That looks like basically a tree of operators. So here we have two input tables. We're throwing away some records, we're doing a join, and we're throwing away some attributes. So this is kind of some abstract representation of that query plan. And it typically gets optimized to say what's going to be the fastest. Now, depending on your system, this kind of abstract tree is going to get turned into some physical model. This physical model is going to specify basically how do I compose this tree of operators into a plan that gets executed. Now there's all these different variations. You know, is it a record at a time? Is it a batch at a time? Is it vectorized? Do I use JIT compilation to flatten things out? Is it push or pull based, right? It's not going to be too important for today, but what's going to happen is we're going to have a plan. This plan gets executed. We'll talk generally about pull-based approach record at a time, but almost everything I talk about today is applicable to other execution models. So here the data flows through this. So in this kind of context here, we have, like I said, the base tables, we're throwing things away, and here we're going to do a hash join. So a hash join, and I'll use hash join as an example a couple times today. You take one side and you build a hash table on it. So you say I'm joining things here. I'm joining on A.id and B.id. So I pick up records from A, I hash them, I put them in the hash table. I do it for all of the records in A. Then I go through B and I pick up a record and I can just, what we say is probe the hash table. I hash its ID, I go look at the hash table and I say, is there any records to rendezvous? Do I want to put them together? And I do this join. I'll do this example a couple times so we'll come back to it. But the important part of this for this talk today is going to be one thing is that for query processing, we tend to think of operators that are stateful. There is some data that gets created as part of this operator, and that data is going to exist and be around. So in this case, it's the hash table. I construct a physical hash table. It sits somewhere. It exists. In databases, it could be on disk. It could be in memory. We don't care. We care that there's state that's persisted, and this state is maintained as I'm processing records. There are also a lot of this plan that's pipelined, meaning a record flows through it, and it's never written down. It's never recorded. It's discarded when we're done with it. So we're going to come back to the state and pipeline execution later, but it's important. Any questions on Databases 101 in 2 minutes? All right, so we don't need to teach databases in the spring. You guys are good. Okay, so we're good. Okay, so we'll keep going. So again, we're in this data set under change. We have regular scheduled queries. Data is changing. So for this context, we're going to think about a query that's scheduled. So here when I say query scheduled, we're basically saying I have some start time, some records are coming in, and then I'm going to execute the query at the end. Basically, once I know that window is closed, like what were the sales for the last hour, I'm going to process it. And we're going to think about latency from the time that that window closes or the time that the last record arrives for that window to the time that I give the result. This is our latency. I know different communities sometimes have different definitions of latency, but this is what we'll use for today. And for the most part, people, because of this eager execution model to do things faster, we're always interested in shrinking the latency. How do I get you to get that answer, but give the answer in less amount of time? That's that eagerness. And if we think about it, it's really a trade-off between resource consumption using computation, memory, disk, I/O, in order to consume more resources to lower our query latency. So eager systems tend to think about, I have some form of state. I have that hash table. And as records are flowing into the system, I am going to eagerly maintain that state. I'm going to take the new records, keep that hash table up to date, probe that hash table, do whatever you have to do to get that result so I can give you the answer fast. Now this is in contrast to those batch systems, those deferred systems that basically do nothing until you ask them. Hey, it's 3 p.m., run this query, hit enter. When you say run this query, hit enter, it then goes and does what it can do. It's going to take longer because it did nothing ahead of time, but it's going to use less resources than that maintaining that hash table as records flow in. Again, I'll talk more about that as we go. What we've been interested in is what's in the middle here. What's this case where I necessarily don't need the most up-to-date results? I don't need like 8 p.m. on the dot, but I have a little bit of wiggle room. What can I do when I care about freshness, but I have a little bit of time slackness? I have some time that I can wait to do things, or I have a window of opportunity that I can exploit. So what exists in between these systems? And for us, I think this has been an open area. And in particular, we've been thinking about, well, how do I use the same amount of resources and drop the latency, or keep the same latency and use less resources? This is a term we've been calling, is basically trying to design resource-efficient databases. If you think of it as spectrum, we're trying to push that curve down as much as possible. We still want to give good performance, but we want to do it without consuming as many resources. So what kind of games can we play? Now, databases is a long field. There's a lot of legacy. We've done things for resource efficiency. So what's been done? Well, people will argue that that query plan a database comes up with is really about trying to use as few amount of resources as possible, because using less resources results in a faster query plan. But that's just that one query. When we start thinking of the system more holistically, when we start thinking about how do we put things together, there's been work on like shared query execution. So, well, I'm going to sit here for a minute, wait to see if anybody else comes in, and instead of reading the sales table once, I'll put these two things together. So I might read that sales table less, and it might make individual queries slower because one person had to wait, or maybe there's extra data that's included that wasn't needed. I overall improve my resource effectiveness, kind of killing two birds with one stone. This is going to be the closest to what I talk about. So individual queries might slow down, they might degrade, but the overall resource usage comes into play. There's been some work on approximate query processing where we can use statistics to derive answers and put bounds on them, or approximate hardware, or approximate computation. I'm not going to talk about that at all today, but you could argue that's another angle on resource efficiency. Virtualization, or putting multiple tenants together to get better utilization of your resources. I'm not going to talk about that today. Hardware accelerators, the design basically specialized operators that can do things like regular expression more effectively than a general purpose computation. Not talking about that. And then there's some work on lazy that I'll get a little bit into, and that's a little bit more. So these are kind of some things that our community has done. But overall, the vision of this work is that there's a need for new database systems, new database architectures that exploits information about quality, performance. What does the user care about? And timing. When do you need this by? What is it going to be run? In order to take this information to improve the overall resource utilization of the system. And we're going to have to do this through holistic integration of basically the whole system. And I'll get more into that design. And that's our vision for CrocodileDB. So why do we call it CrocodileDB? Well, when we were talking about how to do this, we kind of were joking about when you see kind of National Geographic specials, you see a crocodile or an alligator that lays very still, it doesn't do a lot until it sees that it needs to do something, and then it's really fast, right? You see like a crocodile or even a hippopotamus run, it's surprisingly quick at that last minute, but it's not doing a lot to get there. So that was our inspiration. But you also might remember I'm from Chicago, and around this time too, we had a alligator that was in a park that caused a big stir. They called it Chance the Snapper for Chance the Rapper. We don't see a lot of alligators or crocodiles in Chicago, so this is around the time, so it was fun. Okay, so that's this. So what are our design goals? Well, we want to identify what are the opportunities in a system design to allow you to have that trade-off of resources and performance. Like what exists for that in this world? How do we allow users to specify performance requirements that can let us to capture this? What are the signals we can use to inform our decisions? Like what are we going to look for? And how do we integrate these components? Like basically, what are the knobs that we can build and how do I turn these knobs? That's kind of the high-level goal of what we want to do here. And this is CrocodileDB. This is our high-level architecture view. This has all of the things our traditional database has. You have query planner, indices, storage management, concurrency control, whatever that is there. These are the things that we're going to think that are going to be different here. On the bottom, I won't talk too much about it today, is we've been thinking a lot about how does data come in off the wire in a raw form, how do we defer that as much as possible, transform it so it kind of flows through these different state management things. The middle are these different projects, components that we've been building. I'll talk about 2 of them today. And the top are kind of what are the higher level primitives or the concepts that have changed from traditional database architecture. And these tend to be different in the following regards. We have to think about changing how queries get registered. So thinking about when somebody gives a query, can they specify that timing information? This has to be run every 5 minutes, every 30 minutes, or update this when 1,000 new records come in, or what do I want to see when you do the change? Do I want to see the full result every time, or just show me the difference from the last time this has run? So this is something that's different from traditional database systems. What has to happen and is hard is how do we specify those quality objectives? What's the performance objectives or the service level objectives? How do we say what is good for the user? Is it something that's very explicit that says, hey, this query that you're running every 5 minutes or this query that you're running every hour, I need it on the dot or I have 5 minutes that gives us that time slackness that we can exploit? Or can we infer it by looking at the system that says, hey, you run this nightly report, but no one ever looks at it till 8 in the morning. So do I have to run it at midnight, or could I wait till 5 in the morning, 3 in the morning, whatever? And then lastly, we've been building knobs. And this knob is kind of going from these extremes of what happens if I just waited till I had all the data and did it lazy, batch? What if I did it where I ran every record, kind of this continuous query processing of these streaming systems? And can you tweak a knob to kind of do this different trade-off? And we've been thinking about, could you show users this in a cloud environment where they could turn a knob and see what's the impact on their resources, their dollars, versus what's the impact on latency? Because you might have a trade-off there.
In this setting, what do you mean by all the data?
The data for that query. So like if this like for this hour, for this day, we're kind of assuming there's some sort of slice on the data, and that you're issuing that query over that slice. And so there's usually a temporal aspect, but some kind of filter. It could be the historical data just starts to get a little bit harder to do some of the things we're talking about. Is that good?
Yeah.
Okay, great. Next. We need machine learning models, and it's not going to be too much of a crux, but what we really need are models of how the data is going to change. And this should be really clear by the time I'm done, but we need information like models as to, hey, this table over here is likely to get new records, this many, and kind of with this velocity. Because this is going to be the signal that we exploit to make these decisions. We'll need this. And then lastly, we need a dynamic resource allocation system. Databases historically are designed very statically. You define this plan, you give a configuration file that says, hey, this operator has this much memory, or this has this much memory, and it's kind of for the test of time until you change the database and restart it. We've been thinking that this system needs to dynamically take and give away resources as things run in order to make things work. So this is the high-level view of what we're going to talk about, and I'm going to dive into the first project here unless there's any questions at this time. Yes?
You know, there's this inherent need, in the kinds of requirements today for scalability and the ability to exploit the fact that you can predict when things are coming to build scalability. Are you going to talk about that?
Oh,
it's a different dimension from performance and latency, right?
Yeah, it's a little bit, yeah, the scalability, parallelism, concurrency is a little different. I'll get to a little bit, and some of the work that we did I think can be applied to that, so hopefully there's opportunities, yeah, for controlling parallelism in this cost, but I'd say that's what we're actively working on, is how to exploit scaling, and also thinking about it in terms of intermittent resources or spot pricing or things with your capacity changes. Like, how do you do that with that question? So I think that's, I won't get there today, but that's definitely there. Great. Good, any other? Okay. So first, I'm going to talk about this project, intermittent query processing. So intermittent query processing was all about how do we strike a balance of resource utilization, and for this particular problem, it's going to be memory and query latency. And we're really interested in a world where you have some data and you kind of want to see bursty answers over this data. So maybe I'm running it for yesterday and I want to see an updated answer every hour. It's kind of the world. And for part of this, we're thinking about what happens when you have intermittent and predictable data arrival rates. So imagine we have a query that's running. It's a standing query, meaning it's registered and I'm updating the result with time. And we're going to use the y-axis to specify basically how much data there is. Imagine we got a lot of the data, most of the data up front, because maybe it's running over a larger window, and I execute the query. For this graph here, this execution is how long does it take to get the answer, that's that latency. And I give this first answer. Then over time, we start to see that basically there is more records that come in. We see that kind of this records come in bursts. We see this a lot with like batch loading of systems, right? Like data doesn't always stream in, it's some process that runs, here's a new chunk of records, here's a new chunk of records, like whatever it may be, or it could be steady state, but we're kind of looking at this. And then based on some condition, like timing or record count, we have to update and maintain that result. I need to give an updated answer for all of this data. So I execute it based on those conditions. It's an hour, there's 1,000 new records, whatever it may be, I have to update that result and give the user an updated answer. So the question for us is there's idleness. There's a period in time when you're not doing anything. And if we go back to that extreme diagram of continuous do it all instantaneously versus wait, what do you do if you think about these as extremes? These continuous query systems tend to think about the state. Now we talk about state for the queries. It maintains that state. It keeps it. And as these records come in, whatever it is, it does the work to update that state. So it's constantly churning to keep that latency down versus the lazy systems that basically say, I'm not going to remember anything. I'm going to throw away all the work I have. And when I get new records, I'm going to re-execute it from scratch. PostgreSQL, which is one of the most popular open source systems, does this for when you want to have standing queries and get registered when the data changes. So obviously, like I said, we're looking at what's in between here. So the answer might be obvious, but the answer for the question for us is, well, can we figure out what state to keep? Can I be intelligent about what things to set aside, to keep, and maintain, such that I can keep performance good, minimize my resource utilization, while still giving good latency? Like, what's that middle ground? And so that's the key question of this project. We wanted to think about if you had a registered query with a model of how data is changing and some dynamic resource allocation that says, for this interval, this is how much your budget is for keeping state around. What should we do? What things should we persist in order to basically minimize the cost of processing those deltas, those changes, those new records to the data? So it's going to work in this way, and I'll do another kind of refinement of this workflow here. But we have a quick.
If you can go to the places.
Yep.
I want to get a mental. No,
Yep.
please let me go this one. Yes.
Yep.
This one.
Yep.
This one. Yes. So I want to get a mental model of the two things. One is what's the user model here, in the sense that what's the expectation from the end user? Does he want to see the results only at the very end, or does he want to see the results as he goes along?
At some interval. So if it's like a batch, like a today mini batch, it would be what's the number of records that I want to see the change. Every 10,000 new records, give me an update.
Okay.
Or if it's a standing query, I want to see the last 24 hours, but update me every hour. You know, like I want to, so like some kind of, yeah. Like, so for today's sales, on the hour, update me for what it looks like.
Yesterday's sales.
Yes, nor today's sales. So today, imagine today's sales. I want to see at noon, what did I sell? 1 p.m. I want to see 2 p.m. I want to see what I sold. That's kind of the mental model.
I see. Okay. And the other thing is that should we think in terms of like this span of time to be a day or something like that?
Yeah.
Or it's a few minutes or something?
Day, hour,
Day.
yes, day, yeah.
Sure.
But I think the problem still holds, right? Like it's just some amount of data that I'm not going back to the beginning of time.
No, because the reason I'm asking is because the state that you maintain is going to consume resources, and that'll interplay with other basic transactions and queries and
Yeah,
so on, right?
yeah.
So that being the case.
Yes, but it's just a scaling factor, right? Great, thanks. Good? Okay. Okay, so we get a query comes in, we get a plan, we execute this plan has state associated with it, we give our result, right? Again, the state could be persisted and maintained, it could have been a pipeline and thrown away, but this is what happens. What we want to do is we want to figure out what should I keep? What should I throw away? And I want to do this in a way that when I get a change of the data, new data, I'm just going to call it delta data that comes in, new records, deleted records, whatever it may be, I want to take the state of this plan that I calculated and persisted and think about how do I integrate these changes into it so I can give you an updated result. And if I do a good job of picking the right state, I give you good latency and I can compute less resources. Because why would I recompute something that I've already computed, especially if it doesn't change a lot? So that's the key idea of what we want to do in this project. So how do we choose the right state subject to some memory budget? So we need to predict where new data is, and I'll try to explain why. So we need information basically about here's where I'm at, I'm about to execute a query. What do I think is going to change between now and the next time I run the query? And we need to know this, and we want to know two things. Which tables or relations, database people love to use multiple names for the same thing, are going to have new records? And how many records do I think are going to change on these tables? That's what we want to know. Why does this matter? If you think about the example of a hash join, again, this simple hash join where I take some table, I build a hash table of based on this table. Sorry, I'm using table twice. I pick up these records and I probe this hash table. If I did this and I kept this hash table, it's important to think about where are changes going to happen. Because if you were to tell me that with high confidence, new records are only going to come to R and not S, that hash table is amazing. You give me 1,000 new records in R, I just have to pick them up and I probe this hash table to say, do you satisfy my join condition? So I pick it up, I hash it, I look. I don't have to look at all the S, I just look at that little hash bucket, right? So it's highly performant. But if you were to turn around and tell me that, hey, R is actually pretty good, it's very unlikely to change, S is the thing that's likely to have change, that hash table is garbage. Because I pick up new records from S, I now have to go back and rescan all of R for every new record in S. That hash table does nothing. It does nothing to save work. I have to go back and redo something. I save that hash table and it's useless. So if you were to tell me S was going to change, you might want to convert this in some way to maybe be a symmetric hash join where you put hash tables on both sides and you keep them maintained, or you just keep the hash table on the other side. And so that's why it's important when you're making decisions about what state to keep. You have to think about what's going to change, because that's where your work comes from, is maintaining that state, updating that hash table, updating some sort of output, whatever it may be. So that's why we need to know where data is going to change. Okay, so what did we do? We built this thing called DIS, which is our Delta-Oriented Intermediate State Selection. We love acronyms and names, I don't know. Okay, so it's basically, what can we keep? We think about basically a couple of things. We think about state that was created in the original plan, like a hash table from a hash join, so I could just keep that thing, save it. There is state that was never materialized because it was pipelined. It was just thrown through the system and gotten rid of. And so what you can do is you can always capture an operator or a tree of operators by injecting the materialization operator. It basically says, whatever you see, write it down. And so therefore I can just keep it, even though it wasn't originally maintained. Or with databases, we love equivalence. We have operators that do the same thing logically. It gives you the same output, but it creates different state. So I have decisions sometimes about different things to do to create different state that could be saved that's guaranteed to give the same result. So this is basically our candidate when we consider what to keep. These are our options. We can keep nothing too. So how do we implement this? Well, we put this inside of PostgreSQL, but it's pretty generic here. We have a query. We take our unmodified original optimizer, we execute it, we come up with a plan. We take this plan, our resource allocation, how much state can you save, our prediction of where data is going to change, and we give it to this. This comes up with two things. It comes up with a modified plan that's the same result, it's logically equivalent, that might have new state, and then it has a plan as to what state to keep. So you're going to run this new plan, but these are the things you're going to throw away, and these are the things you're going to keep. So we execute the data, we keep this state, we throw away what we're not supposed to throw away, and we keep these things, and this is what we have for that next iteration. Therefore, when new data comes in, that new delta, we figure out how to execute it against this to get the updated answer. If this delta is wrong, we can still do it, it just might be wasted work. But if we pick the right answer, we can avoid recomputation. So if I get new records that come in only to S, I'm able to do the join against the materialization, take this out, do the join against the hash table, and give you that updated result. So I save work, I save resources, I save things without keeping everything around. So that's the high-level idea. So if you understood this, you're good on this part of the talk.
So a question here is how much a restriction is the initial query plan? I could imagine that for complex queries, a different plan might be more amenable to this than others.
Yes, yes. Yeah, good. So Faisal's question has to do with like, what's this original plan? We just kind of assume that the planner is good, and we kind of assume like, which is not always a great question. Like you might want to re-optimize for this delta, and it starts to get into adaptive query processing. We just wanted to start off with saying the original query plan is good enough, and we're going to augment it. Because it's all heuristics in search anyways, but I totally agree we could do this. We kind of punt on this problem a little bit by looking at problems when we have a lot of the data already. So to Sharon's earlier question, I'm executing over the last week, and I start like at, on Wednesday. So I already have a good chunk of the data, so that's good for the data I have. But yeah, if it's like starting from scratch and the data is going to change, you might want a different optimizer. Slightly different problem, but yeah, it's a good question.
I see. Well, but other than that, is also, for example, kind of like the steps of the process. If I put it, let's say, if I know kind of like what I'm trying to optimize, a query plan, not that the workload is going to change significantly, but rather that for the problem of this, it would be a better plan to be optimized through this.
Yeah. We're leaving something on the table by doing this.
But is it a big opportunity? I think that's my question.
Yeah, I think there's an opportunity. It just depends how much you believe your data is going to change over what you have. So like, if it's going to adapt, if it's going to be a totally different distribution, then yes, maybe not. But if you assume that it's kind of roughly going to follow the same pattern, the plan part of it's just to draw, again, like yesterday, draw a box around something and say this is what we're focusing on. Writing an optimizers are the worst parts of databases. If you go to like Microsoft, right? There was a guy, Gertzgraf, who wrote an optimizer at Microsoft 20 years ago. It still runs for most of Microsoft products. There is very few people in Microsoft that can touch that optimizer. Like, it's a black box, it runs, and people are like, don't touch it, it might fall apart on us. So if you cannot touch an optimizer, don't touch an optimizer. Sorry, yes.
Sort of related to that question, the plan optimizer usually has a model of the execution engine and uses that to make decisions.
Yep.
So since you're kind of are optimizing the execution engine, essentially, again, I think that the planner can probably do a better job if it understood.
Good. And so we're going to use the planner for making these decisions. We're going to play what-if games to say, like, so we're still trying to use the cost model and the optimizer to make decisions. We're just making decisions about, well, what if the data changed in this way? With this plan, if I tweak this plan, what does the cost model say? So we'll end up exploiting, through the rest of the talk, I'm going to exploit the existing optimizer and the existing planner to do it. We're just going to tweak, basically, what if for like a search algorithm. Yeah, great. So what you guys are saying totally valid, right? I think you come up with a better answer. Just how much better I can't say.
Yeah, that's
Melanie?
So, carrying what Faisal said one step further, this is for a query.
Yeah.
Right?
Yep.
So, the kind of state in the hash table that you're building is for a query.
Mm-hmm.
Does it compose and it's presumably a well-known query.
Mm-hmm.
So if I have a series of well-known queries, but I don't know when they're going to be asked, I don't know when they're going to be, does this compose?
Kind of, yeah. I'll get to that at the end. So when you code compose, you're talking about multiple queries together and figure out how to overlap it. And
Or not simultaneously necessarily, but they could be concurrent, they could be staggered.
yeah. So I'll try to get to that in the end. We did some work on. I think we had interesting results to show like if you exploit this information, putting things together sometimes is a bad idea, sometimes it's a good idea. You need to know performance objectives and dynamicity to do it, but 100%, we got there a little bit, I think.
So quick clarification question again.
Yeah.
So again the mental model of what the thing is about, right? I'm assuming that in your setup, you're not after a continuous window query at all. You're after a query which requires data from the beginning to now.
Or no, it could not the beginning now. It could be a window.
But the window is pretty large. It's
The
not-
window's large. Yeah,
has
we're
to
not
be
looking
large.
at like 5 minutes. I mean,
Yeah, you're not looking at a
yeah.
continuous query model,
Yeah.
like general whatever, because
Yeah.
this makes sense in that sense.
Yeah.
Good.
Yeah, great. Okay.
So just another
Yeah.
clarification, even though it's a window, is it a moving window?
We did tumbling windows. You could do moving windows. Moving windows makes the problem harder because the state maintenance gets harder to model because you have to figure out how do I put things in and how do I pull things out.
Right.
So we started, the next work I'll get to starts to think about that a little bit more. For this one, it's totally tumbling.
But I think probably for a mental model to understand this, it's better to imagine no window. Like let's say.
Yeah, no window, yeah.
So, like,
Well,
yes.
tumbling windows is almost no
It's
window,
almost
right?
like no
Tumble-
window, yes.
For those that know tumbling window, it's like days, but it's like segmented. Monday, Tuesday,
Yeah.
Wednesday. A sliding window would be the last 24 hours.
Yeah.
So at every hour it moves forth, 23 hours of that 24 hours is valid. So you have to drain some and add some. So it changes the model some. Thanks. Okay, so the goal of this is to figure out how do I minimize the update time, which in theory then reduces our resource utilization, and then also accounting for how state comes in. So I won't get into this too much, especially where we're at timing, but basically we solve this with a dynamic programming problem. If you think about it, you have some query plan, there's a subtree, you're making a decision about do I keep this state, do I discard the state, or do I build the state? And if I do it for this particular operator, there's a subtree that if I do one of these two things, I'm taking away from the budget from the rest of the tree. So that's why it lends itself very nicely to a dynamic programming problem. And so there's overlap, so we ended up, we have a DP solver that thinks about the state maintenance and processing it, and that's the kind of the key insight for the solver inside of there. I can get into it more if they want, but I'd like to keep going to get through the results. And I'll try to go through the results, not too much because this is where you start databasing out. So basically we built this inside of Postgres, we executed it, comparing against throwing away everything. And at the time, which was a state-of-the-art for maintenance, and this state-of-the-art thing is called DB Toaster, and it effectively works through higher order views. Higher order views is if I have some tables involved, I basically maintain permutations of these views. So I think about maintaining R join S, R join, and then you maintain all of these new records come in, and when you have to update, you can figure out which higher order view to pull the data from. Because in theory, you've created all the permutations. I'm going to look at two results. Basically, under an intermittent workload, how does this work? And then if you had a different budget, how does this work against kind of a greedy cache algorithm? So the late data processing scenario we'll do for this particular query is imagine you have a big chunk of the data, 90% of the data, and you have 3 deltas that are getting progressively smaller. So it's kind of like a tapering window scenario. We use a industry standard benchmark called TPCH. It's for analytics. For this first experiment, we set no memory budget. In the next experiment, I'll show with a budget. And we basically say all tables have changes except for the things that are about countries and regions. Those are relatively static. And we're going to report the total query processing time. So how long did it take to do all of this different data? So this is the red bar, and what you can see is compared against the things that maintain everything. This is this implemented in Postgres. This is that thing written in compiled C++ code, the same algorithm, just different execution engines, versus throwing everything away. And so this is the flat queries of TPCH. These are queries that don't have nesting. And because we're doing query latency, lower is better. And so what you can see is that overall, for the most part, the red bar is the lowest or really close to the lowest. There is sometimes that we're not necessarily the best, but across most of these workloads, it's good. There is some cases that its DNF is did not finish. This is the case where basically maintaining those higher order views just created way too much work, and you could not finish in 500 seconds because it's too much stuff you're trying to do. So just right off the bat, it was interesting to say sometimes throwing stuff away and starting over from scratch is actually more efficient than maintaining extra state. So I think this is trying to show the overall case. The next case I think is a little bit more, and this is showing the memory consumption between the two. The next experiment is, what happens is you restrict the budget, because that was my vision, right? Like, you have a restricted budget, you want to use less resources. If we take one particular query, do one particular delta on it, same kind of configuration, and we change the budget, how do we do on latency? The top bar is rebatch. We don't do anything different, so that's why it's flat. You're throwing everything away and starting over from scratch. We compare ourselves against a similar approach, but it's just a cache heuristic. It's a greedy cache heuristic that looks at the cost of making that state and says, what should I save that was the most expensive thing to create? So the differences between us is we're exploiting the changes. So this is a heuristic that has no belief about the future, only the past. So as we increase our budget, what we can see is that there's a point in time where we more or less do the same thing, and there's a crossover point where we start to differentiate between that latency, because we're able to do it with less resources. The dot at the end is that greedy algorithm. It can't do anything until you give it 17.5 gigs. It just can't give an answer because that's the need for all of the state. Okay, so IQP we think is this in-between batch processing and continuous queries. We think it's like a new execution model, new paradigm, where you can exploit timing information. And by exploiting this timing information, we can reduce our memory consumption because I don't recompute things, I save less things. I lower my query latency by lowering my CPU utilization. So I can use less resources to give you an answer without having to save everything. Okay, so that's the first project. Any questions on this before I switch gears? Okay, good. All right. The next one I want to talk about is this idea of incremental aware execution. So going back to the same context, we have a query that's scheduled, data's changing, I give an answer, there's latency. We want to think about how do we shrink the latency. Well, how the systems actually really do this is through incremental computation. You take some part of the data that you have and you compute a result. Then as you get more data coming in, you maintain this result. We call it incremental computation because you try to leverage, you try to build on the work that you already did. And people do this to get the answer in the end quicker. And even once you're in incremental execution, there's a question of how eager should I be? Should I do it once? Should I do it 100 times? Should I do it for every record, 10 records, like whatever it may be? And as you do more and more, in theory, the latency should go down. But what typically happens is you end up doing more work. You're spending more time processing the data, and I'll get to why here in a second. So it's largely due to wasted work. Imagine we have a query that's basically give me the customers that have a balance greater than the average customer balance. That's our query. So we go through, we take our data that we have originally, we compute the average, we find the records that join basically are bigger than the average, and we give our output. So that's a query. We run it, increment, we give our first answer, and we know new data is coming. A new customer comes in. Because a new customer comes in with a balance, that changes the average balance. And because that changes the average balance, there's some work that I did, something I put in this join that was in the end that should no longer be there in the end because there's some part of the query that's not stable. Average changes. And so because this average changes, it says, well, 2 was there before, 2 should no longer be there because its balance is no longer above the average. This new customer's balance is above the average, so it should be there. So the incremental execution wastes work. You do something that's not there at the end. And that wasted work is using resources. So again, back to this trade-off of latency and resources. When we think about a query, the more lazy we are, the higher the latency is, but the less work we do. And as we try to get the answer faster and faster, the resource, the total work you push up changes. And it's a factor of the data in the query. Because if you try to get the latency down and down and you do more and more work, you might be spinning cycles. You might be doing more work that's not there at the end because of just the properties of the query and the data. So when you look at a particular query, it's going to have a different curve to say, you want to go faster? Well, great, I can do incremental work. It's totally monotone. Imagine if I said, find me the customers whose balance is greater than 7. Then every time I do the work, as long as there's no deletes, it's good in the end. That number never changes, right? So it's very query-centric and data-centric that has to do it. And if you go back and look at it, it's not the whole query that introduced wasted work. If we think about, let's say, inserts only, like no customers deleting their data or updating it, but we'll hold for that. Maintaining the average is totally great. Every time I take a new record, I compute that average. That's never wasted work. That's always good work. It contributes to the end. I never throw anything away. It's the join. It's the saying, who are the records that satisfy that join condition is what introduce wasted work. So what we try to do in this project is we say, well, can we take a query plan and chop it up? I won't get into the details of how we chop it up too much, but we chop it up into these paths. And then you can say, well, if you can identify which parts of the query are amenable to incremental execution, well, that's where you should put your time and effort, because that's more likely to contribute to the end without wasting resources. And if you can identify the parts that are likely to introduce waste, spin cycles, and not contribute in the end, those are the things that we should do more lazily. And so with this fine-grained control, you're able to exploit things, try to get performance without necessarily wasting work. And that's the key insight on this work, is this incremental query execution. So it's similar to say we have queries that are registered, we're going to exploit information that data is going to change, and we need to have performance objectives, and I'll get to how the performance objectives here work. Okay. Well, let's start off with this. If you're familiar with mini-batch, this will be very clear. We have a query, it's going to run. Remember, we chopped our query up into 3 paths. So I'm going to use this example here. We have path A, path B, and path C. Calculate the average, join the average against this, and join this. Okay. So then what we want to think about is basically, how many times should I execute this path? And so here, a higher number means I want to do it more times. This is how many times I'm going to do it. You can think of it as temporally. You slice it by, it's for the hour, so I'm going to do it every 20 minutes if it's 3, or if you know I have 10,000 records, it's every 3,333 records, right? Like it's basically an even division for right now. So if we have a query like this, and we have a part that we know is amenable for incremental computation, we do it more frequently. And then if we say 1, it means do it batch. Wait till the end and then execute it, because I only want to execute that query 1 time. So in these cases, for path B and path C, I wait till I'm done and I execute it. With query plans, there's dependencies. Sometimes you have to wait for something else to do it, so that's why they're kind of staggered after each other. Now this is in contrast for how modern mini-batch systems work. If you think of like a system like Spark, they have a knob that lets you do this, but it's for the whole plan. It's all or nothing. As I turn this up, it's saying run the whole query. So if you wanted to run this more eagerly, you're saying do everything 3 times. And the goal is that you can do this and get down to that same latency. You know, you can roughly get to the same end, but can I get to the same latency with doing less work in the middle? And that's what we do by exploiting information about the properties of the query, where data is going to change, and that's what we want to do. Now, targeting latency is a nightmare, right? I know a lot of people in this room know that. So we actually aren't going to target latency. What we're going to do is we're going to exploit the query plan, because the query plan is saying, given a plan, I have a cost model, and that's what we're going to use. We're going to use this cost model to figure out what's our total work, and then at the end, once I have all the data, what does the cost model say to do it? Now they're correlated, but it's hard to say, I want this answer in 30 seconds. But we can say, I want this cost model to say, in the end, it's going to give a lower amount of work. So our problem statement here is, given a goal of how much do I want to shrink the work down. So imagine if I waited till I had everything and I execute it once. It takes 100 units worth of work. That correlates with latency, but again, it's not latency. It's a model of CPU, memory, I/O, whatever. You have a unified cost metric. If I want to cut that in half, I want to go down to 50 units of work versus 100 units of work, that's what we're saying. We want to try to cut that down. Now, a lot of times it is about half the time, but it's not guaranteed to be half the time. So we're saying, given a final work constraint of trying to cut down that work at the end, how do we get there with minimizing the extra work that we do to get there? And that's what we do in this project. So, again, these are proxies. Total work is a proxy for resources. Final work is a proxy for latency. It does work pretty well. Okay, so in QP, we take a query, we take an estimated data arrival rate, and we take that final work constraint. So I just explained, so the query is what to do and over what window to do it. The final work constraint is that ratio. If you wait until the end and you execute it, batch, how expensive is it? And you say, I want to drop it. So imagine you have a query like this. I have a final work latency of batch. I wait till everything, 1. I do it once. I want to get it down to 1/3. So I want to basically cut my latency down by 1/3 versus executing the batch. How much extra work do I have to do to get there? And by being resource efficient, we want to keep this slope as downward as possible. The farther you go out, the more work you did to get to that answer, so you've used more resources to do it. So that's what we want to do. So that's our performance objective. It's a little wonky, but it works. Okay, so with this, our goal is to say, well, I chop up my plan, and I figure out where to invest my resources. What's the biggest bang for my buck? I have money to spend, I have resources to spend, where should I spend them? That's what we want to do with this project. So we're going to do it a couple of ways. We're going to define some notion of incrementability, which is trying to model or capture how amenable a query is to incremental computation. We're going to come up with a cost model to calculate incrementability. And then we have a search algorithm and optimization to figure out, given these constraints, how do I set it? And to your question earlier, we're just going to exploit the existing cost model to do it with slight tweaks. So how do we do this? Okay, so let's think about what is incrementability. Well, if we think about incrementability, we start off with wait till you have everything and do it once. Then if we think about, if I want to go from here to some point, there's a drop in my latency or an increase in my cost. And if you understand that, you understand what we're trying to do with incrementability. It's basically saying, I want to go from here to here. How expensive is it versus how much should I drop it? It's that ratio. So that's what we define it as. If you think about going from some configuration, we'll just start off with the uniform configuration, so every path does the same amount of work. How much did I drop my work versus how much extra work did I do? That's our belief of what incrementability is. How amenable is this for incremental computation? Now, because we're not in one pace for the whole plan, we're chopping things up, this equation has to get a little bit more messy. This is a pace configuration for all the paths. What numbers are we setting these paths to? And it's not the total drop in the end, it's basically thinking about, oh, we have some constraints in terms of saying one path is more eager than another one. But saying basically, for my final work, what was the drop of the final work for one plan versus another plan versus what's the total work difference? But if you understood what I said a second ago, you're good. You don't have to totally understand this. So this is our definition of incrementability, and this is what we're going to exploit. So we have a cost model to say, given a plan of inserts, updates, and deletes, changes to the data, new records, changes to records, delete to records. How much is this going to be? What's the cost model? Can we use that cost model in the query plan to basically play what if? So if I did this versus did I did this, what's the drop in the final work versus what's the drop in the overhead? And then how do I go from where I'm at to where I want to be? And that's it. So the cost model for computing incrementability is a matrix database is usually think of records in, records out. Here we just have to convert it to a record. Records come in, it might result in changes. This balance changes, this average changes, or it might result in deletes because you might be filtering things. So we have a matrix of operators. We have a simple simulation algorithm that I won't get into too much, but basically allows us to use the cost model to plug in this matrix to kind of give out basically our belief. And this is really what's capturing it, because if you're saying, I have a change of new records, and if it results in a lot of updates or deletes, that's telling you you're throwing away things. Because when you update something or delete something, you're saying, I did work before that has to change now. Versus if it's inserts in, it's inserts on only on the out, it's telling you it's monotonic. The plan result mainly changes. So this is how we exploit it for computing our incrementability. So optimization is saying, again, I want to meet a final work constraint, and I want to minimize my total work. So it's an optimization problem. We do it greedily with the search heuristic, where we start off at batch processing. We basically say, does this meet our final work constraint, or do I tap out? We have an upper limit of the work we can do. We say, does this do it? Yes or no. If it's no, we have to think about, well, I have to invest my resources somewhere. Out of these paths I chopped up, I have to say, do I put more money in A, B, or C? And we can do this with with the existing cost model. I say, well, what happens if I bumped it in A? But my clicker is not doing great today. If I increase it in A, if I increase it in B, and I increase it in C, I put those changes in one of these three areas, and I basically see what has the best incrementability. What gets the most down at the least overhead? And we pick one with the highest incrementability, and we just set that, and we just greedily search until, again, we hit one of these two conditions. I either hit what you wanted, half the work, half the latency, or I can't get there because I can't get to what you wanted. You had too ambitious of a goal. I can't do more than 100 iterations or whatever. So we implemented this in Spark SQL because Postgres actually was a really bad idea for the last project, but by the time we realized it, we were too late. So we finished the one in Postgres, we threw it away, we did it in Spark. Because Mike Franklin isn't here, I could say Spark was also a bad choice. So we threw it away and we started over again, but when Mike Franklin's in the room, I have to say Spark was beautiful. And then we basically pipe data in through a streaming system. And our baseline is going to be that uniform what Spark does. You want to cut the time in half, we'll do twice as much work. But the reality is that misses the mark a lot, so we actually use our cost model to figure out how much should I basically do more work to get to where I want to go, and that gives a much better answer. So we're doing better than what you can do with Spark on this. And that's how we're setting the pace, how frequently to go. We do all of TPCH, we have a couple of hand-rolled queries. We changed the scale factor because Spark has to be in memory, and we wanted to push the system's capacity, but we don't want to overflow it because it's not good when you run out of memory. Okay, so we do it on a big machine here. Okay, so I'm going to start off with one query. This is a complex query that's good to illustrate it from TPCH. We're again incremental oblivious. I turn it for everything, or I do it by paths. I chop it up by paths and I do it. So again, we start off with batch. They're both the same because they're doing the same thing. I want to cut the work in half. I want to go down to half the time. You can see that what this means is the InQP, the incremental aware execution, roughly gets to 50. It's not perfect, neither is the other approach. We get close to it, but we're farther to the left. And so because we're farther to the left, this is the CPU time we're measuring. It means I did it with less resources. I was more effective at making decisions about where to schedule my job. And as I go down to 2, I'm trying to be at 20, it should be about 20 seconds. It roughly is. We get there. But what really is interesting in these types of queries is as you want to push it down farther and farther, the gap grows larger and larger. So once you start pushing it, it really starts to fall apart. And this has to do with this query selecting a max or a sum and then joining against it. So it's a really gnarly query that the oblivious approach does a very bad job at. Again, can't hit latency exactly, but I think I'm happy with it. So great. Okay, so if we look at all of TPCH, some queries are just good for incremental computation, so there's no difference. About half of them, there's a difference. So here we're trying to say we're trying to hit a goal. So I said that we're trying to hit a goal. We're trying to say get to 2% of batch. If the cost model says I can't do it, we go to 5% of batch. Those are marked with stars because sometimes the cost model says no and it was actually right. And then again, some of them are smaller versus larger just to press the scale. So here we're saying we're trying to get to that 2% or 5%. How much extra work did I do to get there? So the red bar is us. The red bar lower means I'm doing it and I'm using less resources. The brownish bar is the oblivious approach, which is trying to do it, but it's using more resources. That's what I'm trying to say with this result here. So, and then if we look at, did we actually do it? This is just looking at the latency of the goal. The oblivious approach is, this is trying to show how much were we off from that goal. So the median is saying we were both off by about a second. The average was about 10 seconds off. We were about 2 seconds off. The minimum was no, meaning we both hit the goal. And the max was, in the worst case, it was off by 100 seconds. We were off by 8 seconds. So again, that's that proxy thing I'm trying to justify there. Okay, so InQP is saying, take a goal, make decisions about what to schedule. You can do it and reduce overall performance. I can use less resources to hit my performance goal. So the 2 projects I talked about, incremental computation and IQP, the intermittent query processing, have slightly different scenarios, bursty versus continuous. So these questions that were asked earlier, this I think applies more to that. They're doing kind of complementary work. One is what state to maintain, the other is how to maintain it. There's a whole bunch of other projects that we've published on this I'm not talking about. One was like figuring out what to compute like based on bounds of what can change. Can I defer loading or change how I load? And then Lonnie's question about like overlapping, like how to compose things, we did that and showed that this incrementability is actually really important to understand when you're trying to figure out what should I compose, what should I put together, because if you don't account for that, you might actually make individuals miss their performance goals by wasting too much work. So it's trying to put those things together in order to make those decisions.
Tell me, incrementality in the context of, let's say, as you go on, isn't it data dependent?
Yes, 100% data dependent. That's why we need the models for where the data is going to change.
But then how often are you sort of doing this optimization?
You do, well, yeah. We do it once because for a static set of experiments, but if you were deploying it in reality, that's like a model drift question, I think. So we just kind of did it once and did it. We did some work where we had skew and burst and showed like when you're wrong. I mean, the good case is the worst. If you're wrong, you just use more, you just waste resources or you miss your goal. So if you're in a real-time system and you can't do it and all of the data shows up at the end, you're hosed.
Yeah.
Right? So like if you had this worst case where I can't miss it, the optimization problem is different. But yeah, that's a great question. Okay, and then we've got some active work. So going forward, like I said, we've thrown this away. We've been building a system from the ground up. We're focusing on basically a cloud-native system built in Rust that focuses on state sharing, fine-grained control, escrowed data loading. So how do you do this and kind of defer it? How do we focus heavily on suspend and resume queries? So how do I run and pause? This is a problem we're actively working on. I'm super excited about, where you have like a serverless environment, you have resources, and you only have them for a set of time. So I have a query that's going to take 30 minutes, but every executor can only run for 2 minutes at a time. What do I do? How do I schedule this plan? How do I make it work when I know I only have these short chunks? Thinking about incrementability, state maintenance, and everything on their way. So like yesterday, I did almost none of this work. These people did all the work. So overall, I think this is a great vision. You know, data keeps growing, resource efficiency provides a nice new spin on the problem. Like you don't always have to think about going faster. You can say, I can go slower because I can use less resources, and that's where we're at. So that's it. I made it with like a few minutes to spare for questions. Thanks.
So we have time for a few questions.
We got Pepper in the middle, so they're gonna.
Yeah, so in the evaluation that you showed for the incremental querying, so you're trying to reduce the amount of extra work that the CPU does, but at the same time, when you're doing this, you're reducing the latency of the query at the end. Is that really the y-axis? Is that the latency of the last step, the last
No,
process,
the
or
y-axis
total?
was the total CPU time. So that's the proxy for total work.
But doesn't that mean that even if I'm adding extra work, that I'm actually reducing work?
Excuse me, the seminar is not ending. Keep quiet.
So, but doesn't that mean that although that you're increasing extra work before the last query, in the big scheme of things, you're actually reducing your resource utilization?
No, because you're trying to drop, in this case, you're trying to drop your latency at the end, and you're doing more work to get that answer quicker. Like, the best is to wait till I have everything and do everything,
But
right?
the y-axis is also going down.
The y-axis, no, it was going, so the latency is going down, but the resources are going higher. Sorry, there's two different graphs. I thought you were talking, like, when you're talking about, like, if you think at this graph, right, there's two different graphs. This one is overhead, so this is resources, this is latency.
But that's also in seconds.
Yeah, so I'm trying to drop it down to go from here to there. How much extra work did I do? Versus batch.
I might be missing something.
Okay,
So I think if we wait till the end, then that's the shortest amount of resource time it will take because there's no wasted effort in this case or whatever.
so think about this. You want to clean your house. You know your kids are going to make a mess. Do you wait till your kids go to bed or do you try to clean it throughout the day? If you clean it throughout the day, they drop crap on the floor and you have to re-clean that room again. But at the end of the day, you do it less.
But why is the query latency going down then?
Because that's what you want to do. That was our constraint.
Less clean to be done at the end.
The less clean to do at the end, yeah. How quick can you go to bed?
So that's my initial question. So that is only for the last step.
Last step, yeah, that's latency. That's why I define latency
yeah.
early
It's not-
on,
it's
is
not
this
the-
is latency. Yeah, that's I.
So it's not the total.
No,
yes.
this is total. Well, this is extra versus batch. Any other questions?
Yeah, so what are the architectural in terms of, you said you use Spark, and in terms of cluster,
We did single node on this. Yeah, so then what we're building is for scale out, elastic. Yeah, sorry, I didn't make that clear. It was in my, I was going a little fast, but yeah, and it was all single node for those two sets of experiments.
But from what I've read, CrocodileDB kind of has this model where we sort of briefly alluded to it when we talked yesterday, that we're kind of going back to some of the distributed shared memory principles in terms of how we scale up.
That's what we're trying to do now. So that's what we're doing now. Like we did it Postgres wrong, we did it in Spark because we wanted to do the scaling, but Spark had too many limitations, so now we're starting over again.
So could you tell us a little bit about what's the intuition behind going to that kind of model, which, sort of more the distributed shared memory representation?
Elasticity and cost. I can pay for everything. You want to store this in memory? I can associate with the dollar amount. You want to do this elastic storage? I can put it there and have a cost associated with it. You want to scale up functions? There's a cost associated with it. So we're driving towards dollars versus latency. You want to say, I want to do this and I want to spend $10, we can optimize for it. You want to do this and you want to make it fast as possible, it's going to cost you $100. That's why, because people don't love our models, and we go to dollars and latency, people will get on board. Any other questions?
So a couple of quick, let's see.
Oh, maybe there. One more
We
question.
have,
Yeah,
we'll
we can do one question.
we'll have lunch with it, so
Yeah,
let somebody else
one more
ask.
question from the audience.
I might have gotten them all.
So Sharon, you have the chance to ask one more question.
People are hungry, sure.
So so I was curious, like, do you do the testing, because your plan determination, right, like which one to incrementally evaluate more often is based on a cost model eventually. So how brittle was it to the basically statistics?
Yeah, we did a lot of robustness tests, and as your cost model goes wrong or as your estimates of work go wrong, we do worse and worse, but it's pretty great.
Smooth?
It's pretty great.
Yeah.
Yeah. And for the IQP, it's really important that you predict what tables, not how much. And the answer there is because we're not doing partial state selection. It's a hash table or it's not. I'm not saying save these buckets from the hash table. So if you were doing that, it probably gets a little bit more brittle because now you're saying, I'm trying to model my distribution change.
I see.
Yeah, great. All right.
All right, let's thank Aaron again for the nice talk.